Today's lecture is the continuation of axial force and deformation. So today's topic is about thermal expansion, okay? Thermal expansion, how we take into account how we calculate the forces induced due to a thermal expansion, okay? How we calculate the forces induced due to thermal expansion, okay? So we need to have an understanding on how we can calculate the what do you call the elongation or the expansion induced due to change in temperature. Okay, due to change in temperature, any material would experience any structural member made of whatever material. If you change its temperature, if you raise its temperature, it would experience a sort of expansion, a kind of expansion, okay? So that's what we call a thermal expansion. The expansion that is caused due to change in temperature, okay? When you change the temperature, when you raise it from a certain temperature to another temperature, like from 30 degrees Celsius into 50 degrees Celsius, okay? So the amount of temperature that you have raised, okay, would affect the structural element length, okay, would affect the structural element length. And it depends on how much of change of temperature you have given and what the element is made of, what material the element is made of, and what is the length of that material. Okay. So if we come to the formula, this is the change in length, okay, change in length due to change in temperature. When you change the temperature, delta T is change in temperature. When change in length due to temperature, you see, delta sub T, that means the change that is taking place in the length due to temperature. So we have delta T times L, the original length of the element. So if we have like an element and it has a length, okay, this is an element, okay, and this is its length, L its length, L, this is the length of the element from here to here, okay, this is the element length, okay, L, and the temperature was initial temperature, we call it T1. If the temperature was 30, if the temperature was 30 degrees Celsius, we deal with Celsius temperature, okay, and we have raised the temperature into T2, which is, for example, 50, okay, 50 degrees Celsius. So delta T would be, delta change in temperature would be equal to T, you could say 2 minus T1, and that would be equal to 20, okay, 20 degrees Celsius. That much of change, we have changed the temperature. And the element length, if the length is like 5 meter, 1 meter, it's up to us, the length. So we have the length, we have the change in temperature. What this alpha is about is the material property. This is the property of the material. This alpha is the property of the material. Okay, so alpha is like a coefficient. They call it coefficient of thermal expansion. Alpha is the thermal coefficient, you could say, and it has it means it is equivalent to one strain over one strain, you could say, over one Celsius, 1 degree of Celsius, okay? 1 strain over 1 degree of Celsius. So if you look at this equation, if you multiply alpha by delta T is like we have 20 degrees Celsius, okay, degree Celsius. So the Celsius would cancel each other out, okay, times the original length, which is in meter, if it is in meter, okay. The strain, we know the strain, what is the strain? Epsilon. Strain is change in length over length, delta L over L, right? So if the strain is delta L over L, okay, delta L over L, so that means L would go. So the multiplication, the product of multiplying alpha times delta T times L would be equal to L has gone with the delta L over L. So what is left is delta L. So change in length due to temperature. So that's why alpha times delta T times L is equal to change in length due to temperature. Okay. Do you have any question on this formula? Okay. Just if you know the units of the alpha, then you would know what kind of variables you need to multiply the alpha with, okay? If you know what alpha's unit is, strain over 1 degree Celsius, okay? Strain, 1 strain per 1 degree Celsius. If you know what alpha is, then you know that by multiplying alpha by delta T and L, then you're gonna get delta due to change in temperature. You're gonna get delta L, change in length. Okay, is that clear enough? If it is clear, we move forward. No question about this formula? Okay, so basically we use this formula. This is a material property, usually is given in the question. Okay, change in temperature is usually given. It depends on the question, of course. Original length of element is given, so that we know how much of change the element would experience, delta L. Change in length, how much of change in the length the element would experience due to change of temperature. Okay, so we move forward. So now we have a new formula that is due to change in temperature. What we have over here is an example to see how we could use this formula in this example. Okay, we have, sorry. The example, we have a steel bar shown below, is constrained. We have a steel bar, okay, and it's fixed at both of these two ends, fixed, okay. We have a constraint at A and B, okay. The temperature, initial temperature is 16 degrees Celsius, okay. If the temperature is raised to T2, 50 degrees Celsius, determine the average normal stress, determine the average normal stress. So what is needed is sigma, okay, the normal stress developed in the bar, knowing that modulus of elasticity is 200 gigapascal, coefficient given is 12 times 10 to the power negative 6 degrees Celsius, okay. So we have alpha, we have modulus of elasticity, we have delta T. What is needed to calculate is the stress, the normal stress within AB, the normal stress within AB. Okay, so how we calculate now the normal stress? So normal stress would mean that we need to have the force that is acting along this element, which is the force over the cross-sectional area. Cross-sectional area is given 12.5, so it's square cross-section is given. The only thing that we need to calculate is the force. But we can see that we have change in temperatures. That means the element would expand. If you look at the element, there is no external force acting on the element. If there was no change in temperature, if there was no change in temperature, and the question was asking us to determine the normal stress in the bar. How much would it be if there was no change in temperature? Temperature T1 is 16, okay? And the element is constrained by both of its two ends, okay, at A and B, okay? We have constraint at A and B. And the question is asking us to determine the normal stress. Would we have any normal stress if there was no change in temperature? Normal stress is a question for you to answer. Would we have any normal force or normal stress within the element if there was no change in temperature? If there was no change, can we see any external force acting along the bar so that would cause any kind of normal stress? Is there any force we could see? Is there any F that you can visually see along A and B? Angel?
No.
There's no, so what does it mean? That means there is no stress, right?
Yes. Without the temperature, there's nothing.
There's no stress. So if there is no change in temperature, there would be no force acting. There would be no force acting on the element. Yeah, Yahya.
بس ما مساجر ما سكي درابا أكراوا
Agerchi,
ماس
Nazam Kenagam Chile.
like kilogram
Ah,
20 kilograms.
okay. You mean mass of the element?
أجر ما سكي درابا
Yeah,
لجل gravitational
of course,
نابو force
of course, of course. But now we neglect, is negligible now, the mass is not considered, okay? That's why we say that there is no force. If there was mass, I would have given it as a force, okay, an internal force, or the mass itself, I would have given it in terms of mass. The mass of the element is equal to, for example, 15 kilogram, for example. You convert it into Newton, okay? Anyway, we have no mass. Mass is negligible, is a good point to highlight that if there was a mass, we could have had a force at point B. At point B, there could have been a force due to the mass as a reaction to the mass. But we have no mass, so there is no force if there is no change in temperature. But now we have change in temperature. So that means when the temperature was 16 degrees Celsius, the element was at this length, 610 millimeter. This is the original length of the element. When the temperature has gone up to 50 degrees Celsius, so we have increased the temperature by 34 degrees Celsius. So surely if we remove this constraint, there's no constraint, surely the element would expand, okay, would go upward, right? So there will be some expansion, and that expansion is due to, I could say delta T is due to the temperature, delta T, hold on. Okay, I could say that this is delta, okay, delta T due to temperature. Can I calculate it? Yes. If you have everything is given, like the alpha is given, yes, alpha is given, and you multiply it by delta T, yes, is given, delta T is 50 minus 16, so I have it. I have alpha, I have delta T, I have the original length. Do I have it? Yes, you do. This is 610 millimeter, okay? So I have everything. I could get, what do you call, change in length due to the temperature. But the element is constrained at both of its ends, so at B and A. So there is no way for this expansion to take place. This expansion is not possible to take place. Why? Because we have a constraint at A and we have a constraint at B. So the element is prevented from being expanded at either side, either A or B. So it's not capable of expanding. Okay, which means that the delta that I have got the delta that I have got should be how to say, should be contracted. Okay, it's like we are pushing downward. There must be, if you have a constraint, let me erase this mess. Okay, now I have a constraint. And just now I removed the constraint and I calculated this delta, the change in length due to temperature. Now I have placed back the constraint. I have placed back the constraint. So the delta is not possible for the delta to take place. So what I have now, because of the expansion, there would be a kind of how to say, there would be a delta opposing due to the force, the reaction. Okay, reaction at A, you could say. Okay, reaction at A. There will be a force. So due to RA, there will be a force. If I say RA times L over AE, okay, this would be the delta due to the reaction. Okay, this delta is due to the force. I call it delta F, okay? And just now I said if I have alpha times delta T times L, I could get a delta which is due to the temperature, right? So I have delta due to a temperature, which was possible if there was no constraint, and I have delta F due to the reaction that is induced due to the thermal expansion, which is RA. RA is induced due to the thermal expansion. The element wants to expand, but the constraint is preventing the element from being expanded, and due to that, we will have a force pushing the element downward. We will have a force pushing the element downward. Of course, at the other end, we will have the same amount of force, because for any force, for any action, there will be a reaction. So at B, we will have RB, okay? That is against RA. To be in equilibrium, we can't have a single force. We have to have an action and a reaction so that the element would be in static, right? So for equilibrium purpose, we have a force against RA, okay? And it would be opposite, equal in magnitude, but opposite in direction to RA. So based on equilibrium equation, if we say summation of Fy is equal to 0, we could say that RA, okay, is equal to RB, right? RA is equal to RB, okay? Or we say summation of forces upward is positive. We could say RA is negative because it's downward, plus RB, okay, plus RB is equal to 0, okay? Okay, you will end up again, RA is equal to RB. At the end, the same thing, you're gonna end up with RA equal to RB. Okay, now we understand that we have two forces and they are equal to each other based on equilibrium equation. Now I have said, due to the thermal expansion, due to the change in temperature, we will have a thermal expansion. But the thermal expansion is resisted by a force which is induced. This force is induced due to the thermal expansion. You have a constraint. The constraint will prevent the element from expanding. By what? Preventing the element from expanding by a force, and that force is induced due to the thermal expansion, and that force I label it as RA. So I could say RA times L over AE is equal to delta due to a force, and that delta, so now I will develop the compatibility equation. That delta, which is due to the force, it should be equal to the delta that is due to the temperature. So I equate these two equations. I equate this equation, this formula, I equate it with this formula. So when I equate these two with each other, I have alpha, I have delta T, I have L, I don't have the force, that is what I'm looking for. I don't have the force, I have the original length, I have A, I have modulus of elasticity, so I can get RA. Okay, I can get RA. Okay, how about RB? Okay, RB and RA, they are equal to each other, it's no problem. You just, as soon as you get RA, you will know how much is RB. So you're going to get the normal stress. Normal stress would be equal to RA over the area of the cross section. Okay, so the concept is the same. We have established based on equilibrium equation, you come up with an equation. Okay, we come up with an equation, and based on compatibility, we come up with a second equation. From the second equation, you can get the force. From the force, you can get the normal stress that the question is asking for. Okay, so the concept, the most important thing, how we have established, to know, to understand, how we have established the compatibility equation, okay, or the equation of compatibility. So we look at the questions, the solution, and see how it has been solved. If you look at it, summation of forces along the y, Fa is equal to Fb. That means reaction at A is equal to the force at B. And as long as they are equal to each other, why not just call it F? You don't need to say Fa and Fb because they are the same. They are equal to each other, right? So you just label it as F. Now, the change in length due to temperature minus the change in length due to the force that is induced due to the thermal expansion, okay, this delta is in opposite direction to this delta. This is due to the thermal expansion, it's trying to expand, and this is due to the constraint, it's trying to push the delta downward. So there must be a force against the thermal expansion. So this delta, we make use of the formula of the formula that we have previously studied, which is PL or FL over AE. Okay, the force is due to the thermal expansion. This force is due to the thermal expansion. So you could say that alpha times delta T times L minus the force times L over AE is equal to 0. Or you could say minus delta alpha delta T times L plus FL over AE, because at the end we want to equate this with this, okay? We want to equate these two amounts. So you solve the problem, you get the normal stress. Any question? Do you have any question on this example? If no question, shall I presume that the concept is simple to understand? The concept is simple, if no question. Okay, we have 10 minutes to go. So I just wanted to, the previous example, I found an easy way to explain this example to you. There was this example, okay. This is the last example. I tried to explain it, simplify it, oversimplify it. I found a way, an easy way. If you still remember the example, it was about a bolt and a sleeve, okay, within each other, and we have this knot is moved upward by spinning the knot half spin. Then we know how much of delta. Okay, the point is not this. The point is to understand this thing. Okay, to understand this concept. Okay, when you push the bolt, assume we have now a bolt and is made of, if I'm not mistaken, is made of steel, and the sleeve is made of maybe brass. Okay, so this is the sleeve. Okay, the sleeve, and we have a bolt. Okay, if I assume now, to oversimplify, if I assume now the sleeve is not, the bolt is not capable of neither expanding nor contracting. The bolt that is inside the assembly is not willing to give itself to expand, and it's not willing to contract. The only thing is the sleeve. So when in order for the knot to go up, the sleeve has to contract. The sleeve has to contract. So the contraction would be exactly equal to this amount, which is 0.625, right? 0.625. So if I give like a question to you and I say that the bolt is not contractible and it doesn't experience any contraction or any elongation, okay? If that is the question, determine the force that is induced due to spinning this knot for like one half of spin or one half of rotation, okay? So you calculate this, the displacement, and then what you do is you equate this displacement, which is 0.625, you equate it to the much of contraction that the sleeve would experience, which means F sub S, which is the force in the sleeve due to contraction, times L over AE. Okay? Why? Because the sleeve has to contract that much for the nut to go up. Okay, now if I reverse the order, the sleeve now is not willing to contract, so the sleeve doesn't get contracted. This length doesn't get contracted, which is L. Contracted means that the L will get reduced. Contract means we have reduction in the length. Okay, so if I spin the nut, okay, now we assume that the sleeve is not contracting, but the bolt is elongating. The bolt is elongating. The question is like this, okay? You can't change it. So in that case, we also calculate the amount of this 0.625. This is 0.625, okay? Again, we calculate the 0.625 based on how many of rotation the bolt has gone up and equated to that the bolt has elongated. The bolt, that means F in the bolt has elongated times L over AE. Of course, A of the bolt and E of the bolt as well. Okay, A of the bolt and E of the bolt and L of the bolt as well. Okay, so at this case, if the sleeve is not willing to contract, in this case, if the bolt is not willing to elongate, okay? So we have the equation, the compatibility equation would be this for these two cases. But in this example, the sleeve would contract and the bolt would elongate. So we have both. We have this and that. Okay, we have this and we have that. So due to the contraction added, so that means the contraction will not be the complete 0.625. As you said, as you see here, the contraction was equal to 0.625 because based on the contraction, the bolt has gone up. But and in this case, based on elongation, the bolt has gone up. The bolt elongated so that there would be some space for the bolt to go up. That's how we calculated the force in the sleeve. And B, based on these two imaginary cases that I have assumed in each one of them, that one of them is not willing to expand, the other one is willing to contract, while in this case we have assumed that the sleeve is not willing to contract, but the bolt is willing to elongate, okay? But now in reality, they both, the sleeve and the bolt, they both capable of contraction. I mean, the sleeve is capable of contraction and the bolt is capable of elongation. So we have to include both effects. The elongation effect, this is the elongation effect, and this is the contraction effect. So you take both, so that means FSL over AE, of course, the whole thing is for S, okay? The whole thing has to do with the sleeve, and you add it to F of the bolt times LAE, again for the bolt, everything is for the bolt for this term, and equate it to 0.625. 0.625. I think this would be the easiest way to understand why we have counted the contraction and the expansion. The contraction of the sleeve and the expansion of the bolt, so that the nut would be able to go upward by 0.625 millimeter. I don't know if that explanation would help to understand the compatibility, how we have established the equation of compatibility. Any question? No question? We have 2 minutes for if you have a question. So when you join back, we continue on the thermal expansion. We have 2 questions, we solve them, and that would be the end of our lecture for today. Any question on this new way of comprehending how we have calculated how we have established the compatibility equation? Okay, no? No question. Okay. So let me pause.